Pest is now starting. All attendees are in listen-only mode.
Good morning, everyone, and thank you for joining us for today's webinar, The Pros and Cons of Insurance Pest Management, the new IPM. My name is Julia Freuk. I am the project coordinator here at the Partnership for Ag Resource Management and will be hosting the webinar this morning. We are joined today by my colleague, Caitlin Leahy, project manager for PARM, who will provide a brief introduction. I'm also pleased to welcome our guest speaker, Dr. Christian Krupke, professor of entomology at Purdue University. Before we begin, I'll go over some brief logistics. Please remember to submit questions for Dr. Krupke on the GoToWebinar panel during his presentation. I will moderate the questions for approximately 10 minutes after the presentation. You'll receive an email in the next few days with the webinar recording and link to the webinar evaluation. The recording will also be available on partnershipfarm.org and YouTube. By attending today's webinar, you are eligible for 1.5 CCA continuing education units, 1 for integrated pest management, and 0.5 for crop management. You must be present for the entire webinar to receive those points. If you submitted your CCA number at registration and are watching this webinar live, no further action is required to submit your CEUs. If you're watching this on demand at a later date, please be sure to watch the entire presentation through the GoToWebinar platform and not YouTube to receive credit. If you watch the recording more than 2 weeks after the original broadcast, please email your CCA number to julia@partnershipfarm.org to ensure your credits are submitted. And please make a big note that credits often take a few weeks to appear in your account. If it has been more than 4 weeks, please contact my email. And now, with the logistics taken care of, I'll turn it over to Caitlin.
Thanks, Julia. The Partnership for Ag Resource Management, or PARM as we call ourselves, is one of several projects at the IPM Institute of North America, a nonprofit organization focused on using the power of the marketplace to improve sustainability in agriculture and communities. For those of you who don't know, PARM addresses water quality issues by working with ag retailers to increase sales in profitable products and services that keep fertilizers on cropland. It is our mission to engage farmers and their retail advisors around conservation practices that benefit them both. So why is this important? According to Clean Lakes Alliance, a nonprofit here in Madison, Wisconsin, 1 pound of phosphorus can equal 500 pounds of cyanobacteria. This bacteria is toxic to humans and animals. That means our pets too, when it's absorbed through the skin, inhaled through the air, or swallowed. Even more, this bacteria depletes oxygen, leading to large-scale fish kills that also hurt our fisheries industry. Through sales of practices like cover crops and variable rate technology, we can estimate phosphorus and nitrogen loss reductions that cause these blooms and the resulting economic benefits. These estimates are variable due to factors like slope and soil type, but give our participants the best idea of where they can make a difference. We are able to track sales through annual surveys, and through those, we provide both public reports and confidential nutrient stewardship reports for participants. Check out our 2019 season report on the PARM website. This year, we had 126 ag retail locations participate, representing over 8.7 million acres across 10 states, as well as Ontario, Canada. The report contains practice adoption information, retail profitability, and customer and dealer barriers to implementation. Each of you will also receive the report link in our follow-up email with the webinar recording. Feel free to reach out to either Julia or myself with any questions. And as a reminder, we offer catered educational tools to retail locations that help staff convey the benefits of nutrient management practices to customers. We also offer user-friendly watershed and statewide incentive programs based on available grant funding. You can receive these benefits and many others by becoming a valued PARM member. Visit our website and click Become a Member for more information, or contact me at caitlin@partnershipfarm.org. Also check out our retail member testimonials under our About tab. Our membership program also spans outside of retailers. Support our work to increase conservation practices across the US and Canada through sponsorship or donation. Links are found on our website and will be in your follow-up email as well. As a nonprofit, we rely on your donations and sponsorships to keep our project moving forward. And with that, I'll turn it back to Julia.
Thanks, Caitlin. As Caitlin mentioned, we provide free resources for ag retailers, grower clients, and consultants. On the left is our 4R approved agronomist handbook, available free for download. We also develop these locally and regionally for individual locations with our membership program. Our phosphorus loss reduction wallet cards in the lower left corner can be ordered for free on our website. Our next webinar will be in August, exact date to be determined. Look for announcements in your email, on Facebook, and Twitter. And remember, we take into consideration your suggestions for webinar topics, so be sure to fill out our evaluation form after the webinar. Today's webinar is sponsored by Crosse Seed. We will now hear from Scott Woltman, cover crop lead and agronomist at Crosse Seed.
Good morning. Hopefully everybody can hear me okay.
Yep, it sounds great. Scott, go ahead.
Thank you. My name is Scott Woltman, the cover crop lead and agronomist for Crosse Seed. We are excited to be sponsoring this webinar today, given the audience and the content of the presentation. So Crosse Seed is a distributor of cover crop, forage, turf, and native grass seed, headquartered in La Crosse, Wisconsin. And we have distribution sites all across the upper Midwest. We've been in business for more than 100 years, taking pride in having the seed you need when you need it. But we deliver much more than seed. We strive to deliver resources our customers count on and agronomic insights the industry has grown accustomed to using in the field. There we go. You may recognize some of our brands. Tillage radish is probably one for sure that most folks on the webinar heard of for sure. Because we partner primarily with ag retailers and seed suppliers, it's important that we deliver sound agronomics and always lean on the information we already know and acknowledge versus so much of the anecdotal recommendations that exist, especially around cover crops. One thing is for certain, our team is always learning with the goal of helping our customers and their growers. The Crosse Seed footprint in dark green is broad, and it's enabled us to partner with so many retailers across the Midwest and in other areas that have deep conservation history with programs and initiatives already in place. An axiom that we live by is to always be planning ahead. In order for conservation practices to work, planning early and often is a must. Seed is obviously important, and in recent years with prevent plant pressure, I think we're all learned that getting seed spoken for early is often a good practice. Also important is planning out equipment and labor needs. But none of this works very well if the cultural aspects aren't prearranged and fully considered. Today we'll be hearing about pest management. We also ask our customers to consider herbicide interactions, crop rotations, nutrient cycling as well, and how the system can and will be changed by adding conservation plantings. Our team has tools to help based on years of feedback from our customers, shown as one of our past webinars on herbicide rotational restrictions with cover crops. Beyond that, Crosse Seed takes pride in being known for the resources we offer our dealers and their growers. Management guides, tech sheets, agronomy bulletins, and decision trees, to name a few. We even offer customized tools to further help our retailers connect with producers. Soon we'll be shipping out bioassay kits to customers who ask for them, along with plot seed, so dealers and growers alike can take a closer look. And don't forget The Dirt is our periodic newsletter that provides timely, quick hitters based on what's going on in the field, as well as in the conservation seed industry. You can find us by going to lacrosseseed.com. Again, thank you very much for your time this morning, and we look forward to the webinar today. Thank you.
Thank you, Scott, and to all of Lacrosse Seed for being our sponsor today. And now we'll get the presentation started with Dr. Christian Krupke, Professor of Entomology at Purdue University.
Okay, thank you, Julia.
Okay.
What I'm going to talk to you about today is a summary of some work we've done, most of it at my lab in Purdue and with collaborators elsewhere in the Midwest, reviewing kind of where we are with an insect pest management in field crops. And there I'm talking more about corn and soybeans than some of the others. I recognize there are other field crops as well, but I'm going to mostly talk about corn and soybeans today. Okay, so as we all know, corn and soybeans are our largest commodities in the U.S. We plant 90 million acres of corn, 77 million acres of soybeans every year. But the trends I'm going to talk about today in terms of where we're moving as how we manage insect pests are common to many other cropping systems as well. So my examples will be from corn and soybeans, but you can readily apply them to most of the other crops that you can think of. And namely that most of our pest management is done from an insurance mindset, from an insurance perspective, meaning that we manage for pests in a way that minimizes risks and ensures that we cover as many pests as possible ahead of time without monitoring and without thresholds. Now, you can probably, if you're in the Midwest, you're probably seeing some green on your part of the US map here. And all this reflects is that what we do in corn and soybeans affect one another. So it's not universal that we're rotating these two crops, but it's fairly common. There's of course continuous corn as well, and sometimes corn is rotated with other things, but and soybeans as well. But for the most part, we have a corn and soybean rotation, or corn and or soybeans are planted in most of these acres throughout the region. And so when you think about what I'm going to talk about in terms of my examples and what we're doing in these crops, remember that from year to year, although the crop may change, a lot of the practices are very similar, and I'll elaborate on that in a minute. Talking about corn specifically, you see in this graph here, this shows how much of our corn is BT corn, or it's sometimes called GM corn or transgenic hybrids. 85% is BT corn. And why is that important? Well, with that BT corn, we are targeting the key pests of corn. So things like corn borer and the western corn rootworm. Those have historically been the two biggest insect pests of corn. And BT corn hybrids have effectively managed both of them. There are some resistance issues that have popped up, but by and large, these approaches have been successes. They've reduced levels of insecticide, and they've allowed increased worker safety. They have a lot of benefits of BT corn. Most of our corn is BT corn. That means most of our corn acres are protected against most of the key pests. However, my bottom bullet there shows all BT corn sold has neonicotinoid seed treatment applied. And I'm going to refer to that by the abbreviation NST for the rest of the time today. And neonicotinoids are going to be a large focus of the talk. They are the largest use of insecticide worldwide, but nowhere are they used more than in the US. And I'll give you some statistics here. So a little bit of chemistry and a background on these compounds. The two diagrams on either side of the title there show the two common seed treatments we use, thiamethoxam and clothianidin. They have many trade names, including Poncho and Cruiser and others, but those are the active ingredients, and I'm going to refer to them repeatedly here. So a couple things to know. They're very toxic, and the reason we talk about them in terms of non-target effects, you've probably heard some of the controversy about honeybees. That contact LD50 that I have there on honeybees means that if you dissolve what's on a single corn kernel, if you dissolve that active ingredient into a sugar solution, let's say, you have the potential to kill hundreds of thousands of honeybees. That doesn't mean that we do, of course, there'd be no honeybees left if it was just a matter of planting corn and killing bees. That's not what I'm getting at. But what I am saying is that you need things to go exactly right if you're not going to have these non-target effects. These are highly, highly toxic insecticides. These insecticides are orders of magnitude, tens or hundreds of times more toxic than some of our older classes of insecticides to honeybees and to other insects. And they're not specific. Unlike the BT corn example I gave, which attacks specific pests and are harmless to things like honeybees, neonicotinoids are not that way. So why did we adopt them so readily? Why are they so widespread in the environment? A couple of reasons. Low vertebrate toxicity, and that goes to things like worker health and human and safety and so on, and high water solubility. So I'll talk a lot more about the water solubility, but that just means they dissolve very easily in water, and therefore they move very easily into plants with water. However, they're also persistent. We can find them in Indiana, in some of our work here, in field soils up to 3 years after planting. So although they move with water, they hang around in the soil and don't break down very readily. Now, this is a chart that I've seen presented by USDA. And it only goes up to 2010, but the trend is probably similar. We're generally using less insecticide is what the message they're trying to get across. They're going back over 20 years here, or almost 20 years in this chart. And you see how much insecticide we used to use compared to now. We all like that shape of the curve. Nobody likes to think about using more insecticide. But this is a very, what's the word? Unhelpful graph in a way, because it's giving you, look on that vertical axis, it's giving you pounds per planted acre. How much by weight insecticide we're using. It's declining. Well, that doesn't mean much, because when you think about insecticides, what's the important factor you want to know about them? Not how much they weigh, it's their toxicity, their killing efficiency, how many insects they can kill, or whatever your target organism is. You want to know how toxic the material is. So if we put it in those terms, we have very different graphs, and those are shown here. And this is from a paper that was published last year, and the citation is the bottom right. You can have a look at it online. It's an open access paper. And these figures are taken directly from there, and you see as we go up through the 2000s, we see this dramatic rise in the levels of insecticide toxicity as measured to honeybees. And that's figure 7 is on the left there. You can see when we get in the early 2000s, we start using neonicotinoids on corn and soybeans, and it goes way, way up, and it's still going up. On the right, you see the crops that are responsible for that big rise. And that will show you that most of what we're seeing, most of that rise is attributed to corn and soybeans. And those are shown in the blue and the red, respectively, parts of those bars. Okay, so one of the first set of experiments I did was looking at honeybees' exposure to neonicotinoid seed treatments. We were getting reports of bees dying around corn planting, and our bee biologist at Purdue at the time, Greg Hunt, he called me and he said, "What are we applying to corn that's killing bees?" It was in April, about 10 years ago. And I said, "Nothing. We're not applying insecticides to corn right now. We're planting corn." And he said, "Well, I've got dead bees." And so what we see with honeybees, this blue line represents when honeybees are collecting resources through the year. And you can see that peaks in right around now in the early summer days, and then it declines as we get into fall, and of course through the winter months there's not resource collection generally. So when bees are flying through the air, they build up a static charge, the same as you would if you shuffle across a carpet. and then you can touch someone and give them a shock. Bees build up a charge with friction as they fly through the air. There is friction there as they move through the air. It's not as much as shuffling across a carpet, but it's still there. When they then land on plants, they're charged, and that charge causes pollen to be attracted onto their bodies. So you can see this bee here is covered with pollen. It will then scoop that pollen into the pollen baskets on its back legs, you can see in the other photo. And then that's pollen is one of the main food sources for bees. So bees only eat two things: honey, or rather nectar from plants that they make into honey, and pollen. Pollen is their protein and fat source, and the nectar is their carbohydrate source. So they get both of those from plants. So this building up of a static charge is a good thing most of the time for bees. But as I'll show you in a moment here, it can also be a negative in some cases. So this is taking us back to corn. This is the period of typical corn planting in Indiana. I took the average date of corn planting across the past 10 years or so in Indiana, and I bracketed in here. So you can see it goes from mid-April, and in some cases like last year, 2019, we're into June with our corn planting if the rains are not cooperative. Okay, this little video here shows you something you're all familiar with if you've seen corn planting. Most of our corn planters are what we call air planters, which means they use air to move seeds and to singulate seeds on seed discs and have reliable planting at the chosen plant population. They're great engineering feats, these planters are. But when you're using that much air, using a vacuum planter, as it's also called, an air planter, pneumatic planter, all synonyms, you have to exhaust that air. And what we found is that in that exhausted air, we were also exhausting fragments of seed, sometimes microscopic abrasions from the seed coat. And you all know probably that corn seed is usually green or yellow or pink, depending on the seed coating. What we would see is that whatever color that seed was, our exhaust material would be that same color. So what we wanted to do after that is look at how far that material moved beyond the planted field. And you can see the diagram here. That cloud there is just showing how that material moves beyond the seed and whether that material is toxic to the honeybees that it made contact. How far does it move and how toxic is it? So we knew that we were carrying the materials that were on the seed were being exhausted. We just didn't know how far it was going. And you can see I've diagrammed here some honeybee hives, and you can see the foraging radius is written in here. I'll talk more about that in a second. Again, you can look more online if you want to read this paper, but what we did there is we just took our hive locations that we accessed online at a program called FieldWatch that you may be familiar with. We took the crop type data, so we looked at corn, other land covers, and we looked at our wind velocity because we wanted to see how much does the wind move this seed treatment, these residues around. We know that bees move around the landscape, so if you get deposition onto flowers and you're not in an apiary, that doesn't tell the whole story, right? Because bees will move across cornfields. And if you're a bee in the Midwest in April or May, you're probably going to be crossing corn and soybean fields while they're being planted. Almost all of our corn and soybeans, all of our corn and the majority of soybeans are treated with neonicotinoid insecticides. So that dust from those planters will contain those neonicotinoid insecticides. So what is the hazard there? Is that something we should worry about in terms of our bees, even if they're not located right beside corn? So this is Indiana, and you can see all the red is corn. All the red dots are corn, and you can see the Hoosier National Forest in Indianapolis in the center and lower part of the state are, of course, not corn areas, but for the most part, if there's not a city there, not a large urban area there, or national forest, we've got corn, especially in the northern half of the state. The blue dots are our apiaries that are registered, and we draw 1.4 kilometer or just under a mile foraging radius there, because we know the bees will move at least that far. And then what we're trying to do, we're going to ignore that static charge component, even though that's very important. We know that when bees are statically charged and they fly through a dust cloud, whatever's in that dust cloud will be attracted to them. But we're trying to be conservative here and give a best case scenario, so we ignore that static charge. And then what we're trying to do is we say, okay, if we sample around fields for 100 meters, how much deposition, how much material do we get in terms of this neonicotinoid dust? How far does it go? So this schematic just shows when we looked at how far foragers move, they're leaving the colony, that's a cornfield, and around that cornfield we know the zone of deposition. I didn't show you all those data, but we did measure how far the material moves, and it moves beyond 100 meters of the planted field. So it moves a fairly far distance. It moves farther when the wind is blowing, of course, than it doesn't, than when the wind isn't. But in any event, even on relatively still and windless days, we get a lot of movement because we're pumping this material out with these powerful fans from these planters. So it's getting up, and it's moving beyond the planted field. So what we found is that the vast majority of bees will encounter that toxic dust during planting. When we first worked with neonicotinoid seed treatments, it was thought that that would solve the drift problem, because you've all seen planters, sprayers, either aerial sprayers or ground sprayers applying liquid pesticides, and you see that drift of those droplets. We always try to minimize that, but it will happen. Neonicotinoid seed treatments were marketed as eliminating that drift problem. It's on the seed, it's not going to get off the seed, it's not going to drift. Well, that's not the case. We do have a lot of drift of these materials. They move significantly beyond the planted field, and they are a hazard to bees. It doesn't mean it kills every bee that passes through it, but it does mean there's a lot of intersection between foraging bees and these residues. Only 1.5% or so of the Indiana apiaries are outside the deposition zone. So the reason I mention that is because when this first was documented, there was a suggestion, well, move your bees, move them away from the planting area. If your neighbor's planting corn, move them. Well, what this suggests is there's nowhere to move them to. If only 1.5% of the bees are outside the deposition zone, that tells you that most of Indiana, and also that map I showed you a couple slides ago, tells you most of Indiana is under the influence of these compounds. There's nowhere to move them to. You can't move your bees to Montana for a couple of weeks during planting time. It's not reasonable. So moving bees is not an option. So what we've recommended to producers or to beekeepers instead is to close off the entrance with some hardware cloth or some mesh. Put a sprinkler on the bees. If you just have 1 or 2 colonies, just put your sprinkler so it doesn't move, so it's continually raining on the bees. They'll think it's raining and they'll stay in for the day. You know, they'll get crabby and they won't like it because they want to go out, they need to collect food and water and so on, but it's better than them flying around and encountering these residues. We've been working on this for the better part of 10 years, but we still have issues. We had another bee kill this year. We don't have that problem solved by any means. There have been some, there's been some marketing around some other dust reduction technologies and so on, but they haven't been widely adopted. We don't have a lot of use of them in the marketplace. So we're still using a lot of insecticide on our seeds, and a lot of that is moving off the seeds and into the air and into the water onto adjacent ground. So when you buy a corn seed that's treated with neonicotinoids, you buy a certain amount of chemical on that seed. What we've focused on the past few years is try to measure how much of that gets into the plant, how much of that moves off the plant, and where does it all go? Environmental fate is what we call this. So this is a schematic of a corn seed that's treated with neonicotinoid. As you guys all know, corn seeds are not corn colored. They're not the color of popcorn, for example. They're usually pink, purple, some color that lets you know it's been treated. So about 2 or 3% of what goes on the seed is lost during planting as that dust. What we want to know next is how much goes into the plant. That's where we want it. We want it in our corn plant to protect that plant against insects that may come along. And I'll talk about what those insects are a bit later, in case you're wondering. So what I call this is the pest management window. And we did this at one site in Indiana a few years ago. We took a DeKalb hybrid with naked seed, which you can't buy. It's not widely available. It's not available at all in the marketplace as far as I know. Fungicide only, which again, you can't buy. And then the low rate and the high rate of what was called poncho at the time, clothianidin. That's the major compound used on corn seeds still now. It has other names, and the names have changed. So I'm not going to get into all the trade names, but the point is this is the major compound used on corn. What we did is we dug up plants throughout the season, every 3 days throughout the growing season. The root, the shoot, and the seed were homogenized and the neonicotinoid content measured every 3 days. This was work that my graduate student, Adam Alford, did, and we published this, and again, you can look at this online, but I'm just going to summarize those results for you now. These 3 graphs show what we found in the shoot and the root and the seed, respectively. And along the vertical, the y-axis, we have how much clothianidin, how much of the active ingredient of neonicotinoid is in that plant part. And the days post-planting, how long after that seed hit the ground, is along the horizontal. So you can see we go from 0 to 20 days. And what you'll know right away is that we have a peak. We do have it moving into the plant tissues, okay? So that's good, but it very rapidly declines. And by the time we're 2 or so weeks out, we don't get much of this material in the plant tissues. We don't know if we're still killing insects at 5 or 7 on micrograms per gram here. I don't know that, if that kills insects. I have my doubts, but let's say we do. Let's say if we have a non-zero level, we're still getting pest management. That's a pretty short window. If you don't have a pest insect show up, try to feed on that plant in that window of time, you can't get a pest management benefit. So when you buy these neonicotinoid treated seeds, you are buying a pest management window that is a matter of days to a couple of weeks. It's not long. So the reason I emphasize that is so that you don't have a false sense of security about, months of protection or season-long protection or anything like that. That's not the case. This is the shape of that curve. It's what we call an exponential decay curve. It rapidly declines, and that decline accelerates after that initial peak, okay? We will always have that shape of a curve with a compound like these neonicotinoids, and the reason is water solubility. So I'll give you a bit of chemistry here. I promise it won't be too long or too painful. So what this represents is water with 3 different compounds in it: low solubility, moderate, and high, okay? Low solubility just means if you mix a material into water, it doesn't go into solution very easily. You can't mix too much of it in, okay? It'll settle out. It just won't dissolve in water. An example of that is a common insecticide we use called Warrior. That's probably one of the most common insecticides out there, a pyrethroid called lambda-cyhalothrin. Only 0.005 milligrams per liter. It's a speck on the tip of your finger. It's not very much. Moving up to moderate, about 10 times more water soluble is atrazine. You've all heard of atrazine. It's still a big player in corn weed management. It's about 10 times more soluble. But now let's look at the high category. And now we have neonicotinoids. Clothianidin, 270 milligrams per liter, so thousands of times more soluble than the others, and thiamethoxam, which is tens of thousands, hundreds of thousands of times more soluble. So this is the reason that these materials will keep showing up in water, and I'll talk about that in a moment. This is also the reason that when you plant a seed and you have this coating on the exterior, that the first thing the seed does when it hits the ground, it starts to imbibe water. That water enters the seed, it goes through the seed coat into the plant, and it carries with it what's on the outside of that seed coating. Now, once that plant is saturated at, let's say, day 5 or day 7, that plant is loaded up, no more can go in. Just in the same way as if you dissolve some sugar in your coffee, at some point you can't get any more in. What's going to happen to that seed treatment? It's going to move off the seed coating and away from the region, away from the plant, okay? It's not going to stay there all season and just trickle into the plant in day 10 and 20 and 50 and week 7 and 8 and 9. That's not how it works. It goes into the area of low concentration, follows the water, very water soluble. So this here explains that quick uptake and the short residence in plant tissues. Okay, so how much of that went into the material, went into this plant for the whole growing season? How much of what we put on corn seed winds up going into the plant? Only about 1 to 2% in total was taken up by the plant. So it's not a very efficient way to get insecticide into a plant. It sounds like it would be, but it isn't. And that reason is that extremely high water solubility. Once the plant is saturated at any given time, no more will go in. The plant has to grow to get more in. And meanwhile, if it's still raining, this material is bleeding off the surface of the seed and moving, and we'll show that in a moment. So we know that more than 90% of what goes on the corn seed is not accounted for yet. Where does it go? That's the next part of the story here. So here you have an overhead view of the Purdue Water Quality Field Station. And you can see we have these plots. We've got 12 plots laid out here. We can plant them with corn or soybeans or what have you, and we can put whatever regimes we want on there. Under each of those plots it's built over a clay box, and the water that falls on there is discrete. So we don't have movement of water between these two, between any two plots. So what we want to do here, these are called lysimeters, by the way. What we want to do here is collect water from under that plot. There are little stairs going down under the plot for each of these. We want to collect the water under this plot and analyze what's in that water. And again, this was work done by my graduate student, Adam Alford. He would go down and he would collect the water that fell onto each of these plots and analyze that water for the detection of neonicotinoids all through the season. In fact, he did it for a full calendar year. What we wanted to know is, when do these materials come off of the seeds and move into the groundwater, into the water table, and at what concentrations? And here are some of those data, and these numbers won't mean much to you, but I'm just showing you these time periods. This is from a few years ago. June and July of 16 and 17, that's when we have our peak movement off of the seed. So well after planting time, this material is moving with water away from plants into the tile drains and wherever the tile drains into. So those concentrations there, I will show you more on those in a moment and what those concentrations mean in terms of biology of some of the animals that they might come in contact with. But that's the peak period. It's in early summer. So we moved out from this in collaboration with some researchers, Jason Hooverman's lab at Purdue here. He's in the forestry department. Did a field or mesocosm study. What a mesocosm is a cattle tank, a cattle water tank that we use, and we put water in there and we fill it full of whatever organisms we're interested in looking at. We can make a miniature pond in there. So you get some algae and some dead leaves and some tadpoles and some water bugs, and we're trying to duplicate a mini pond, okay? And what we're trying to do here is mimic the effects that some of these insects might have by introducing representative levels of pesticides to them. So when we did that, we found a few things. Oh, I should back up. We also looked in the field and we were trying to detect levels of neonicotinoids out in the field. We wanted to see, if we look at ponds in Indiana, even ponds that aren't right beside water or aren't right beside corn or soybeans, do we find neonicotinoids? So the answer to that question is that we found them everywhere we looked. So not surprising, after all I've told you about the water solubility of these compounds, that we would find them everywhere. They move readily, they move with tile drainage, and water, of course, moves in ways that isn't apparent when we're standing at the side of the field looking above ground. Sometimes it's moving underground in sort of counterintuitive directions. We can't see everything that's going on under the ground, but what we know is that these materials show up in ponds and lakes and streams. Now, we also know that aquatic insects are highly susceptible to clothianidin in water. And the way we know that is we did some of these mesocosm studies, and we documented how much of this material was required to kill some of our representative insects. And it's not much. It's a few parts per million, as you see here. Now, here you have some aquatic insects. You have at the top a back swimmer, below that a water boatman, and below that a water tiger. These are not very charismatic insects. Nobody's going to fly a flag to save these insects. They're not cute, they're not fuzzy, they're not appealing like honeybees in any way. A couple of them actually bite and are nasty when you pick them up. But what we see when we look at the concentrations that are required to kill these insects is, look at this chart here, and you can see what I've done here is all those data that I showed you from the water quality field station are represented here. And you can see we're up in the 2, 3, 4, 5 region. Sorry, just one moment. Okay, sorry about that. What you see here is all of the data that I showed you earlier from those water quality field stations, and you can see we're in the low single digits. Okay, now I'm going to give you some context for that. In June and July and August, when we have a lot of water insects active in creeks and streams, is when we have a lot of those neonicotinoids entering the system. And here you have that water tiger I showed you in the last graph. That line there is the lethal dose to that insect. And you can see that many of our detections are above that line. So it's not unreasonable to assume that we're probably killing most of these insects that we're encountering in the field at that time. So this is how we have the intersection with water quality. Now, are these insects that are pollinating our crops? No, they're not. Are these insects that we want to see more of? Not necessarily. Most of you have probably never seen this particular insect or anything. But we know enough about ecology to know if you're starting to have an effect on these kinds of insects in the water system, eventually we're going to get to some organisms, and in terms of effects, those effects are going to reach organisms that we do care about, and that we do use and want to have a value associated with. Things like migratory waterfowl, ducks, and so on, many game fish. You cannot have, the system will not stand as long as you're wiping out a large portion of it. Let's say some of our aquatic insects numbers are reduced by pesticides or by whatever it is. Could be any kind of a stressor. You will eventually have effects moving up through the food chain. We know that lesson from many other examples over the years. So this is just one example, and we don't know what this means yet. We don't know how many of these insects are being affected. For all we know, most of the effects have already been seen, and we can't document them anymore because we've been doing this for 15 years in terms of the seed treatments. But what we do know is that if you're looking for insects and want to document effects of neonicotinoids, don't look at the pests that are the target. Look at these aquatic insects, because they're getting the most exposure for the longest period of time. The most reliably exposed insects are probably going to be aquatic insects that are not pests, don't even have any intersection with corn or soybean crop. Okay, let's summarize this water part. The vast majority of what is applied as a neonicotinoid seed treatment never enters target plants. Most of it ends up in the water. So aquatic insects are the most exposed to neonicotinoids. There are some lethal exposures, and aquatic plants are a sink for neonicotinoids. Now, one of the things we need to figure out, our study looked at how much of the material was coming off of seed treatments through the season. And we found in June and July that we had levels that would be toxic to some of these aquatic insects. We don't know that what aquatic insects live adjacent to that field in those in those drainage ditches. That would be the next step. But what we do know is that if water tigers, for example, live in those drainage ditches, they would be exposed to those levels, and you would expect some of them to be killed by that runoff from neonicotinoid seed treatments. Here's an aquatic plant we've looked at. You've all seen duckweed on the surface of creeks and streams. That plant picks up neonicotinoids very readily. I'm sure other aquatic plants do as well. So that water solubility comes into play again, because you have water that has an insecticide in it that moves into solution readily. It can move into those plants too. What effects does that have, if any? Is that something that we should care about? So this is just food for thought on that one. Now, all of that water solubility means that you'll also have the material in plant nectar and therefore in honey. This was a study that was published in the journal Science a few years ago. This lab sent their staff of their lab all over the world. Whenever they went on vacation, this guy asked them to bring back some honey. And so they went all over the world and collected honey and brought it back. And then all they did was analyze that honey to see if neonicotinoids were in the honey. We know they're very water soluble. We know plant nectar is usually, not usually, we know that plant nectar is mostly composed of water, and that nectar then is concentrated down into honey over time and becomes more and more, becomes sweeter, and it's sort of a fermentation that goes on. So what they found is that 3/4 of the samples contained at least one neonicotinoid, 45%, almost half, contained 2 of them, and 10% contained 4 or 5. So this doesn't mean that there are any human health worries or effects. They didn't measure that or even really talk about that. All this demonstrates is that even in plants that honeybees are visiting, which are generally non-crop plants, in most cases they're feeding on plants that are incidentally there. We don't raise large numbers of plants just for honeybees to produce honey. But they're coming in contact with these materials. So it's showing up in the environment, quite prevalent all over the world. So this just shows that water solubility in a different way. We looked at it as well when we looked at, a few years ago, Elizabeth Long, a postdoc at the time in my lab, did this project where we looked at water solubility and measured it by finding the pollen of bees that were near or far from agricultural plantings. And all we did here was put in a pollen trap at the bottom of each colony. As you see in this slide, that little drawer there pulls out so you can collect the pollen once a week or however long you like, whatever interval you'd like. And you can see in the lab here where Dr. Long laid out all the different pollen colors and sorted them out for identification, because we had 2 goals here. We want to identify the pollen species, what plants were bees feeding on, and we wanted to identify whether there were any pesticides in that pollen and what were those pesticides. Are they important, and which ones should we target? So we had 3 sites, a natural area, kind of more of a pristine, relatively speaking, as far from corn as we could get and still be in the region. An untreated cornfield, in other words, no neonicotinoid on the seed, and a neonicotinoid treated cornfield. I'm not going to show you all those results. Again, you can read this paper online. You can see the citation there at the bottom left. 2 sentinel colonies at each site, and we sampled the bee collected pollen for 16 weeks, from May to September, so through the active period of foraging, and we did this after planting was over. And why that is important is because we don't want to have that dust factor in here. We want to say, okay, what if we solved this dust problem? What if we had a way to not have corn planting dust contaminate the landscape? Do we still get honeybee exposure to neonicotinoids and pollen? In other words, are they getting it from the plant itself? So what we did here is collect all this pollen, sort it, extract, and analyze the pollen with liquid chromatography and tandem mass spectrometry. It's just a very high resolution way of analyzing for a wide range of chemical residues. We're not just looking for neonicotinoids, we're looking for everything at this point. The pollen subsamples were identified using microscopy, so I'm going to show you a little bit of what we found there on the species of plants. And again, we're looking at insecticides, fungicides, herbicides, and we're looking for everything, not just agricultural compounds. We want to know what's there. Our limit of detection is fairly high resolution, 0.01 parts per billion. So we can find very small amounts of pesticide. Just because we find it doesn't mean it's important in terms of a lethal dose. So we took it a little further to quantify what the risk was, and you can read the paper to get those details. But what I'm going to show you today now is just a snapshot of those results. The first thing I want to show you is, we're just going to focus on one site, the treated cornfield, and you can see that what bees feed on is shown by these different colors in the graphs. And you can see we have the yellow around the middle is trifolium. That's your clovers. And there's another clover that's purple, and there's another one that's denoted by a light a lighter purple and a darker purple as well. And these are your white and your red clovers. Bees like those, they're common in agricultural environments. You can see corn on the bottom right of the legend there is the green with the blue, or rather with the black pluses in it. And you can see they do feed on corn pollen. They feed on soybean as well. But all this is trying to show you is that they feed on a wide range of non-crop plants, what we'd call weeds. Plantain is a common weed they feed on. They feed on asters. They feed on some trees like cottonwoods and poplars and so on, that pollen. So they have a wide range of things that they'll find to feed upon. So when we took that same pollen and we analyze it, and we're looking for insecticides, we find a couple of things. On the far right, you'll see all this purple here. This is an insecticide that has no agricultural use. It's an insecticide that you would use in residential or homeowner applications called phenolphthrin. Okay, and that was our highest detection and our highest hazard to bees. The other thing I wanted to point out here is where I've got this line is that's our clothianidin spike. Look at the date on that, 20th of June. So this is before corn is flowering, well after planting. And this is showing up in some of the pollen of plants that are not crop plants. So this is just another way of documenting that these seed treatments move out beyond the field and are then encountering bees. Is this a lethal dose? No. They could feed on this and not be lethally exposed, but it also doesn't mean it's innocuous. It doesn't mean it does nothing. It means what I'm trying to show here is that it's there and it's beyond planting time and it's in non-crop pollen. So after all of this, this work and other work that I haven't shown here, we developed this schematic here that shows you how honeybees are exposed to pesticides. And there are many ways that that happens. They're kind of summarized here. The point of this is to show you that if we have water-soluble pesticides, if we have pesticides that we plant using a pneumatic planter that move off the seed, we have lots of routes of exposure that would have been counterintuitive or not even thought of 15 or so years ago. But now we're seeing them routinely and we're documenting them. So we're learning, that's the good side of things. We're learning what the routes of exposure are and how to mitigate those. And there are a few, some of them are more addressable than others. And let's talk a little bit though about the benefits of neonicotinoids. We're doing this all over the United States. Again, almost all of our corn is treated, the majority of soybeans. What are the benefits? So if you look at the seed treatment label for neonicotinoids, you'll see many insects on the label. This is just a little subsample of a few of them. But there are more than this on the label. And some or all of those insects may be present in a region in a year. But just because they're there doesn't mean they rise to the level of a pest. And we have some information on that now, just in some of the newer literature that's coming out. I'm going to show you some work we did a few years ago. We did get some naked seed to work with. We haven't been able to get it since then to make these comparisons. So that's why if you look 2012 to 14, you'll say, well, these are old data, and you're right. I would like to continue this work and expand it and do more of it. It's very difficult to just get the naked seed in the elite hybrids, in that good germplasm. So for organic producers, of course, that can be done. It's much more challenging in conventional corn hybrids. So let's say I want a naked seed that has Bt and has glyphosate tolerance, but I don't want any insecticide on it, or I want fungicide only. That's a difficult thing to get in the market. Very, very rare. So you can see our three treatments here: naked seed, low rate of clothianidin, and high rate. And what we're doing is we're collecting the stand counts, plant heights, root injury, which will measure damage by the corn rootworm, and yield, which is the all-important, of course, for most. And I'm only going to talk about the yield results here, but again, these data are summarized in that 2017 paper that you can read if you'd like. Here's our first yield slide from 2012. You can see the naked seed is in the yellow, poncho low rate in the pink, and purple for the high rate. No statistical differences at any of our farm locations. These are small plot trials at Purdue Research Farms. This was a drought year, if some of you may remember that, if you're wondering. But it was a drought year, especially in the southern and central parts of the state, and that's reflected by these low yields at those locations. The following year, again, no statistical differences. You can see these yields are all very similar. In 2014, again, no statistical differences there. So you may be thinking, well, what's going on? Why aren't we seeing anything? And I think the reason is the pests are quite infrequent, quite uncommon, and the pesticide is not in the plant for very long, as I showed you earlier. It's just a matter of days, probably maxing out at a couple of weeks, but I don't even think it's that long that we're getting pest management from these approaches. Soybeans, I'm going to talk a little bit about. We also use neonicotinoids for soybean aphid control and control of other soybean pests. We did a regional study a few years ago to determine, again, that pest killing window. We looked at soybean unifoliates and trifoliates through the season to look at thiamethoxam content. That's usually called cruiser. Many of our soybeans are treated with cruiser. Cruiser Max is the trade name. And what we're trying to do is look at the intersection of when the insecticide is in the plant tissues and when soybean aphid populations are high, because we want those two things to intersect. We're not going to get good soybean aphid control if there's no insecticide left in the plant. Here you can see our growth stage and our days post-planting. We're going up in this part of the table here up to the V2 stage. So that's 2 trifoliates, and we're going up to 18 days post-planting. And you see our treated versus untreated. This is the amount of thiamethoxam, the amount of insecticide in the tissues. And you can see we're sky high in the VE and VC stages. The cotyledons themselves are very toxic, of course, loaded with insecticide. But you can see that it's starting to drop off very rapidly. That's what that plant looks like at that time in the field. But for the rest of the season, we don't have significant differences. So by the time we're at 20 days post-planting, we don't have significant differences. I don't know if we're killing pests at that V1, V2 stage, or at that, we don't have those data. What we do know is that we don't have significant differences from V2 onward. When we get aphids in Indiana, it's usually at R2, R3, which is not even on this table. So what I'm saying here is that by the time aphids arrive, a soybean is a soybean is a soybean. There's no benefit in terms of soybean aphid control with typical population curves of that insect. There's no benefit for most of Indiana in that case. If you get soybean aphids coming in very early, which you do in some areas, including Wisconsin, you may get some efficacy there. But we don't typically see that in much of the Midwest. Our big soybean aphid time historically was in early August, and recently we haven't gotten much pressure at all from the aphid. It's really equilibrated to a level where it's very rare that we would have a treatable infestation, where we would have over economic threshold of 250 aphids per plant. So this schematic sort of shows that lack of intersection between those neonicotinoid concentrations and when we see aphids. The red triangle, though, shows the declining neonicotinoid concentrations. They peter out around V2. We have aphids coming in the late V stages and the R stages of the plant. So there's not a good intersection there. We published a study last year where we looked at yield data, and this was led out of the University of Wisconsin. Sean Conley, the soybean agronomist there, and his postdoc led this work, and you can see all the locations we looked at. All we're doing here is comparing the results from all of these over 11,000 plot-specific yields, and we're asking the question, do we get a yield benefit from neonicotinoid-treated seed in soybeans, fungicide-treated seed? And what we see on this one is, well, let me just talk a little bit about what we did in terms of the economic analysis. What we're going to do is we're going to look at seeding rates of 100,000, 140, or 180,000 seeds per acre. And we're going to look at a variety of soybean price scenarios. And if you know the soybean prices currently, we're currently in the lower end of that. So if you have a higher soybean price, you will take more risk in terms of a pest management input. If you have a lower soybean price, it's less likely to pencil out. That's what we're trying to reflect here. Our seeding rate is typically going to be, most fields are going to be planted around that 140, but we went below and above just to compensate for that. And so what we're trying to do is see what is our likelihood of getting a profit under these different scenarios. And again, this is summarized in the full paper, which you can access online anytime you'd like. It's shown here. And what we see is that we have, numerically and significantly, slightly better yield here, but we call that negligible, as you see here in the title, because when you allow for the fact that it costs money, there's some cost associated with applying the soybean insecticidal seed treatment, and you work in the fact that we have relatively low commodity prices, you don't have a likelihood of getting a benefit from it. Most producers won't realize any benefit from applying this insecticide to soybeans. And management practices in this study had a greater influence. In other words, fine-tuning your seeding rate, getting things like that right, agronomic type of considerations. This chart here, I'm just going to direct you to the middle graph, and that shows, if you look at those yellow symbols toward the bottom, that shows you what is our break-even point. In other words, how much under the conditions that we've spelled out here, 8 bushels per acre in the yellow, how much should the soybean seed treatment cost? And the answer is it shouldn't cost very much, because there's not much benefit to be realized here. It's very difficult to get that to pay for itself, is what we're saying. Now, there's a more recent study, just came out last week or the week before, on yield benefits. It was commissioned by New York State. Cornell researchers put that out. They looked at 908 trials in corn and found a higher yield in 99 of them, but in the vast majority of them found no difference. In a few of them, they even found a lower yield. So that again reflects that most of the time we're not likely to get a benefit. It's very difficult to find a yield benefit, again, because the pests are uncommon that you're targeting and the insecticides are short-lived. So is this what we would call IPM? This is the IPM Institute that's putting this on, so we should talk a little bit about IPM. What's the definition? This is the definition that's in a textbook that I've used at Purdue in teaching a class. Here's another definition that's found online from the University of Minnesota. You can read those if you'd like. I'm not going to go through them, but what they're trying to do is they're trying to integrate information about pest populations, what's the likelihood of them being there, with the value of the crop and the non-target effects you may have. We all want to have this quality environment. We also want to maintain the area in and around the field for subsequent crops for subsequent years. So that's a part of the calculus here. But if you look at other sources of information, you'll see that neonicotinoids are key to IPM solutions. They're very valuable. Their benefits are many. Now, these are some of the key registrants that are marketing these seeds, and they have these definitions that include neonicotinoids as indispensable. That's another point of view. Clearly, that's what the market is doing, because almost all corn and the majority of soybeans are using these products. So these yield benefits that we don't see are not telling the whole story. There is a peace of mind benefit to having an insecticide on the seed and saying, well, now I don't need to count these insects. I don't even need to worry about it. I can just apply this pesticide and be done with it. And if the insect shows up, I'll be covered. And that may be true, and that may be the approach that's going on here. We know from survey data, this is a publication from, again, a few years ago in Pest Management Science, that shows that IPM practitioners get their information from mostly those top 3 categories here, accounts for almost all of where they get their information: a crop consultant, a seed or chemical company rep, or an ag retailer. Myself, I would probably group in with university extension representative. We're down under 10%. So where you get your information is important in how you define IPM and what you decide to do about it. And we see that most people are not getting their information from their neighbor or university extension rep. These top 3 categories here, in some ways, in some cases, could be collapsed into 1 or 2 categories. So why aren't we doing more IPM? Why is it this way in these crops? Well, there are some real barriers. There's some real challenges here. These pests are under the ground, and they're difficult to monitor. They're difficult to track. So that means that it's easy to market something toward these pests when you can't count them or see them. You don't even know if they're there. It's very different than Japanese beetles that are chewing up your soybeans. Well, you can see them, and then you spray them and they're dead. It's very simple, even to somebody who's not doing a full research study, to quantify the benefit. If you have something that's underground and you never look for it, have never monitored it, never see it, it's very difficult to determine if you're getting a pest management benefit. What are the numbers? What are where are the thresholds? We have knowledge gaps on abundances and field histories. What I would say, though, is that we know enough from the data that I showed in terms of yield to at least infer that the pests aren't common, and we also know that most of our thresholds are outdated. And by that I mean that the thresholds we use are, many of them are from the 70s, 80s, maybe the 90s, usually earlier. That's before corn and soybeans were nearly as vigorous and competitive as they are now. These plants are difficult to stop. They're difficult for these pests to get a foothold on. We need to allow for that, and we don't. We don't allow for plant tolerance at all. So there's a fear, and so marketing is based around the fear of using other or older insecticides like pyrethroids to replace neonicotinoid seed treatments. Well, the neonicotinoid seed treatments didn't really replace anything. So they in turn probably don't need to be replaced. Remember, our BT corn hybrids are still work and pick up the major players in terms of corn insect pest management. For soybeans, when we have in-season outbreaks of things like aphid, that's still managed primarily with in-season foliar sprays. We're not getting much bang for the buck from neonicotinoid seed treatments. So the replace thing here is it's a bit disingenuous to say we're replacing neonicotinoid seed treatments when they themselves didn't really replace much of anything. They didn't displace some of our old soil and liquid insecticides as much as the BT technology did, particularly in rootworms. So the yield benefits are rarely seen. We don't document our pest pressures. So that's a problem in terms of the classic definition of IPM. We know that neonicotinoid seed treatments do offer a short window of protection. The material does get into the plant. We also know that target pests are uncommon. There's no reason to think that they're more common now than they ever were. In fact, there's a reason to think they're less common. If you have good efficacy from these seed treatments, and we've been using them in all the corn and most of the soybeans for about 15 years, their densities should be a lot lower than they were 15 years ago. There's no reason that we can conjure up why their densities should be higher, because it's been a very difficult environment for them to survive if these seed treatments are as efficacious as claimed. But these two factors, the short window of protection and few target pests, combine to explain why it's hard to get that yield response. If you have the target insects encountering a toxic plant, you'll get a yield response. You'll get good pest management. We have data sets that show that. These products can work, they do work, but most of the time there's no opportunity because the pest densities are just not there or are not there at the right time. On the other side of the non-target side, and when we get into water quality questions, we know that these three factors, the almost universal adoption, high toxicity to non-target organisms included, and high water solubility means that we have to be careful. Universal adoption means that we got a lot of exposure to other organisms. So environmental stewardship will remain a challenge. It's going to be hard as long as we do pest management this way in field crops. So where do we find the common ground here? Well, I think most of us would agree that we want to safeguard that food supply from pests. We want to maintain a quality environment. Those are both universal goals. I think nearly universal, maybe universal, although nothing's universal, I suppose. One solution is just to reduce the proportion of seeds treated with insecticides. I've been saying this for years. It's done nothing. The amount of insecticide per seed has only gone up since I've been working in this field. We're using more than ever on corn seeds, and there's no movement to reduce that. I believe if we offered those elite hybrids and soybean varieties with and without neonicotinoid seed treatments, you would see in-field comparisons. You would see curious farmers and people involved with the ag retail side that would want to know and would say, I'm going to plant this side by side on my farm. I'm going to see what pests are here. I'm going to see what happens. That's not widely available. The market does not have a lot of options for you if you want an elite hybrid and you don't want any neonicotinoid seed treatment on it. But that would allow for actual field histories, actual pest pressures to be documented. You are not going to be able to document it if you don't have any differences across the field. You cannot see what your pest management approach is doing if you don't have a control, if you don't have an untreated control. You have nothing to assess it with. And as those data are coming out, they're showing that we don't get a yield benefit in most cases. I think we'll see more and more data that continue to reinforce that, but there's no substitute for someone being able to do it on their farm for themselves. And I think that's something that if we move toward a truly free and open market where we can get access to these hybrids without neonicotinoids, I think we'll start to see those measurements, those quantifications of where do I need this material and where do I not. Okay, and with that, I will end. Have some time for some questions, and yeah, let's take it from there. Thank you.
All right, thanks so much, Dr. Krupke. So we will be accepting questions from the audience. We're going to give everyone 2 to 3 minutes to send in questions. So go ahead and enter your questions into the question box on your screen, and then we'll be back on to answer those questions in approximately 2 minutes.
Okay, I'm going to step off for about 2 minutes.
All right, we're going to get started with the Q&A. Everybody, please feel free to keep entering questions as we go along. And the first question we're going to do is if it affects aquatic insects, has there been any studies done on mosquitoes? Are they mitigating or adjusting to neonicotinoids?
Yeah, that's a good question. The short answer is no. I don't know of any study on mosquitoes. Trying to think. No, most of the studies that have been done on some of the insects that live on the bottom, under rocks, in the detritus in the bottom of streams. Those insects are exposed to the highest rates of neonicotinoids. Mosquito larvae move in the water column, so they would be exposed to less of it than those bottom feeders. I think that's one of the reasons we focus on those bottom feeders, and also because those insects, those bottom feeders, are what we call environmental indicators, because they are more sensitive. They're the insects that things like trout and other game fish feed on more. That's where most of the work has been done, but it would be interesting to see how mosquitoes do. That would be a nice silver lining, I guess, if you're killing a lot of mosquitoes in all these streams and ponds with these neonics. But I don't know of any work on neonicotinoid in water and mosquitoes.
Okay, next question is, with the economic environment that we are in now, we are seeing a small shift to non-BT and conventional corn. This is going to increase the use of insecticides being sprayed on corn. How do we handle this? The insects didn't go away and we will need to spray.
Well, you will need to spray for some insects, but for many you won't. And I can only speak about Indiana, which is where I work and live, and there is a move to conventional corn. You're right about that. And here, our BT hybrids take care of corn borers and western corn rootworm. And the numbers of those pests have been low, especially western corn rootworm. So producers that are moving to conventional corn here are not having to spray or use insecticide for western corn rootworm in some cases. They are monitoring and spraying for corn borers. So yeah, it's not perfect. We're not able to move away from BT hybrids and replace them with nothing, because those two pests I mentioned are serious risks and you have to monitor for them and adapt to them. But what I would suggest is that the populations of those pests are in many cases and in many regions are at historic low levels. And so with monitoring for them and managing that risk, I think it's a better time to move toward those conventional and monitoring and threshold-based approaches than it would have been certainly 10 years ago or 15 years ago, when in particular the rootworms were at a very high level of pressure. And when I was here working here at Purdue at the time, the pressure was much, much higher. You couldn't dream of having an untreated corn plant out there for rootworm. But now it's totally different. We hardly see any of it in our untreated checks. We have a hard time finding that high pressure. And that's good news, because that's the key pest of corn, there's no question.
Next question is, it seems there are quite a few people using in-furrow fertilizer application methods. Would this not be a simple way of applying insecticides instead of using neonicotinoids?
Well, that in some crops that's done. They do apply neonicotinoids that way. But if you're talking about other insecticides, we have for years, before we had the BTs especially, used in-furrow applications of liquid insecticides like pyrethroids, organophosphorus insecticides, either as liquids or as granulars. So that's been done before. That has a lot of issues in terms of worker safety, and it's not a very precise way of delivering insecticide either. You're basically putting down a bed of insecticide or a glob of liquid insecticide, and you're putting the seed on top of it. It works and it provides protection, but the non-target effects and worker safety issues make it less appealing. In terms of neonicotinoids, there are some crops where they apply in furrow as well, but it doesn't offer any advantage over applying it directly to the seed, really, because in both cases you need that water, and that water will carry it up into the plant, but of course the water will also carry it away from the plant and out of the field. So the short answer to your question is the in-furrow approach doesn't really address some of the issues with neonicotinoids if you apply neonicotinoids in furrow. If you go to the other insecticides, you're back to some of the problems and reasons, rationale of why neonicotinoids were introduced in the first place.
Next question, are we seeing any pest resistance to the neonicotinoids?
Yeah, there are a couple of examples. They're in the south. The one I'm most familiar with is in thrips in cotton. It's been documented. I think there are probably going to be a lot more cases reported, just because we're using them so much in so many areas, and you have pests exposed to, as I showed you, varying levels, including very low levels. One of the best ways to get resistance to a chemical is to apply levels that are sublethal, so that insect does get some exposure, not lethal exposure. It's able to reproduce, and you can that way build up tolerance in a population, because you're not killing them all, but there's still enough exposure that there can be some weeding out of the susceptible population. So we don't want that, but that's the way it's going to be with neonicotinoids, because the exposure is not consistent and at a high dose. So there are some white flies as well, and a couple of aphid examples in terms of resistance to neonicotinoids. I think you'll see more of it, and I think where you'll see it first is in those sap-feeding insects, like aphids, like white flies, and so on. The ones that are the most exposed and feed directly on the sap of the plant that has neonicotinoid in it.
Okay, next question. You mentioned the accumulation of neonicotinoids in the duckweed. What concentrations did you find?
I can't remember offhand. Yeah, I could look it up, but it's not a good use of time for you. I would refer you to our paper online. Again, it's in the Environmental Science and Technology, and the authors are Alford and Krupke, Krupke. And you can see those exact numbers. I don't want to lead you wrong on that. The main thrust of that paper, the main message on the duckweed side, was that the duckweed will, within 24 hours, uptake whatever is in the water that it's grown in terms of neonicotinoids. So if you put a high rate of neonicotinoid in that water, the duckweed will very rapidly take that up. And it's not too surprising. That's a plant that, sits right on the surface of water. It's a, very relatively small, simple root system, high surface area to volume ratio. So it becomes saturated quite rapidly. But the numbers I can't recall, but I would refer you to the paper, and you should be able to read, even if you don't have access to the full paper, you should be able to read the abstract online. It's Krupke and Alford, and I believe it's 2019 or 2020 publication. I think 19. Environmental Science and Technology is the journal.
Next question, how do seed companies respond when asked why they don't sell non-treated options?
The most common responses are our clientele. Farmers don't want it. If these products didn't work, they wouldn't use it. These farmers are informed consumers. The benefits are there. Statements along those lines. Another one that I've heard is that to offer all those new products, in other words, take all the corn hybrids and theoretically double the number of offerings if you're offering it treated and untreated, is just undoable in terms of the economy of scale of it. It's too troublesome. They would need all these new SKU numbers. It would be an inventory problem, and the demand isn't there anyway, so why do it? I've gotten those kinds of answers. The most common, though, is that everybody wants neonicotinoids on their seed. The only people that are advocating for something else are these people that are not farmers, people that are researchers and don't know what farming is really all about. That's the most common response that I hear.
Next question. I think you mentioned that the neonicotinoids could be found for 3 years in the soil after use on crop. Is there any chance any of that was dust deposition? How long does it take for neonicotinoids to break down in the soil or become less toxic?
Yeah, that's a good question. I don't have a short answer for you, so I'll give you a slightly longer one. On the dust thing, which was the first part of your question, the dust that lands on soil, on surfaces, on trees, probably breaks down fairly quickly, because the one thing where neonicotinoids do break down quickly is UV light. And that dust is going to be a fairly shallow surface layer that when it's subjected to the sunlight, those products will break down fairly rapidly. So I don't think planter dust is a huge component of what we find when we do these core samples in the soil, because we're digging down a few inches now to get these samples. So those are samples that are protected from light because they're down under the soil. They're getting zero UV exposure for years and years. The temperatures are also more steady down there. So how long does it break down? That depends on the soil type. There's one publication from a soil, from a very low organic matter soil in Canada, where there's 13 years or something was the half-life of the material in soil. Our study was 3 years. We were still finding it. So it can vary a lot. But when you think about persistence and you say, is this compound, is this pesticide persistent or not? There are many ways to measure that. One of them is water solubility. One of them is groundwater ubiquity. One of them is binding the soil. I don't want to get into all of that other than to say that neonicotinoids would be on the persistent side. So we're talking years, and we're not talking weeks before they break down. So how long would it take depends on the soil, depends on the organic matter, depends on a lot of those factors, but it's definitely not confined to the growing season and in the few months after that. So I wish I had a number I could give you, but it does vary widely. We know that much.
Next question, were seedling comparisons done in no-till environments? Our comparisons with no fungicide on corn seed had a dramatically lesser stand count.
Okay, yeah, no, that's a good question, good point. We did not do those comparisons in no-till. I would, as I said, I would like to get sufficient seed, treated and untreated fungicide only, every one of those combinations, to do it in no-till and to do it following cover crops and to do it in conventional tillage, which was what we did. But as I said, I just can't get access to the seed. But I don't doubt that you would get a range of answers depending on tillage, depending on pest pressure, depending on cropping history. And I think we would like to get some of those answers, but it's been difficult to do that work. To get to that level of resolution is where we ultimately need to get to.
All right, and next question, do you expect to see increased label restrictions with neonicotinoids?
No, I don't see that any of that is coming. I don't have too much inside information in terms of EPA or anything like that, but I do know enough from the people that I do talk to there to know that there's no real move to have any additional restriction. The trend at EPA recently has been to roll back a lot of regulations across the board, including in pesticides, and I don't expect any restriction. Restrictions have been in place, as many of you may know, in the EU for some years, in Canada as well. But in the US is unique in that we're the only country where the use rate of neonicotinoids has gone up substantially in just the last few years. Since some of these non-target concerns came to light, we're using a lot more of them. So I don't expect any of that to change. I don't see any restrictions or reductions or anything. If anything, I would predict we're going to use more and more. We'll eventually see neonicotinoids replaced, I think, with other chemistries like diamides is a newer class of chemicals. But I think that that will be probably a voluntary choice by the registrants. I don't see any government regulation or restriction. They've been reviewing this for a long, long time, and nothing has changed. So I don't expect anything to change.
Okay, and the last question we'll do, and you did touch on this a little bit, is would you look at in-furrow insecticide like Capture instead of the neonicotinoids?
Well, we have a large database on capture from years past, mostly looking at corn rootworm for that. That was our consistent pest, the main pest we could find. We haven't done much of that lately just because the market has not really demanded that type of efficacy work. The other reason we haven't is we don't have many pests to speak of. If you told me, I would like you to look at capture insecticide against wireworms, white grubs, etc., I would not be able to find a field site to do it. And I have told the registrants when they come with some of these trials, I can't find you a high pressure site where I can guarantee that the insecticide will be challenged by pest pressure. So the pests aren't there, and we just haven't seen a lot of move in the market toward that. If either of those things change, yeah, certainly we would do it. We've done it before, worked with that and many other insecticides for years, and we're set up to do that kind of work. But we would need the pest pressure to be there to get a good challenge, really, to get a good challenge to the chemistry.
Okay, and in the interest of time, I'm going to wrap up the Q&A. Thank you so much to everyone who sent in questions, and for those of you who we didn't get to, I can forward along those questions to Dr. Krupke. So thank you so much again for joining us today, Dr. Krupke. We really appreciate you taking the time to share your work with us.
Okay, thank you.
At this time, I want to recognize our premier Ag Retailer members, Gold members, the Andersons, Country Visions Cooperative, Millborn Seeds, and Saddle Butte Egg. And Silver members, Garrity Egg, Pandora Grain and Supply, Lacrosse Seed, and Nutrient Egg Solutions. Their contributions help to make this webinar possible and help promote the strides that ag retailers are making to reduce nutrient impairments. For more information on membership and all the benefits that come with it, contact Caitlin at partnershipfarm.org or visit our website and click Become a Member to fill out the online form. Finally, I'd like to acknowledge additional funders and collaborators that made this webinar possible, in particular the McKnight Foundation, Great Lakes Protection Fund, and Lacrosse Seed. If you are interested in sponsoring future webinars, please contact me at julia@partnershipfarm.org or visit our website. Help us keep these webinars and other resources free by making a tax-deductible donation to PARM. By giving just $50 today, you can support this webinar series that provides the ag community with the latest research on nutrient management from experts across the United States, as well as continuing education units to crop advisors. I'd like to thank our recent donors, the University of Toledo's Department of Environmental Sciences, Keys Seed Service LLC, and Mark Ruddy. Go to partnershipfarm.org/donate to contribute today. We will also send a donation link in our follow-up email. As we wrap up, please remember to look for the follow-up email in a few days with the webinar evaluation and webinar recording. If you submitted your CCA number at registration and are viewing this webinar live, or the recording within 2 weeks of the original date, your CEUs will be automatically submitted. Only if you watch the recording more than 2 weeks after the original broadcast date do you need to email your CCA number to julia@partnershipfarm.org to ensure your CEUs are submitted. One last reminder to please take our webinar evaluation. It's a great way to let us know what topics you want to hear about on future webinars. I want to thank everyone for joining us again today and hope you join us for our next webinar.